I was just going to summarize very briefly what happened in the first lecture, and then I'll move on to the next subject, just because I noticed I was also a little bit chaotic towards the end. So just to give you I'm not going to derive anything, but just kind of give you a little bit of the overview. So we were talking about this Chern-Simons formulation of 3D gravity, and basically there were two things that were mentioned. The first thing was the role of boundary conditions and the definitions of charges. And so we were decomposing the connections in this way. And in this part of the connection and the spatial part, we were putting the information about the charges. And in the time component, basically, you have to view it as the component of the connection that contains the sources. They're related by the equations of motions. But here, which I'm writing them just in the static case, just for simplicity, because I'm lazy. But of course, it's not difficult. You just have to put a differential if it's not static. But in any case, just for the black hole case, just that the commutator of the two connections is 0. And this connection that contains the charges is as well the connection that contains the information about the boundary conditions, and in particular, in the case of interest, what does it mean to be asymptotically like ADS3, quote unquote. And so this A phi, basically this notion of boundary conditions where we have something like ADS3, we were writing it in the case of SL2, you would put something, you would say the connection behaves, this is the part that is what you would have called the ADS boundary. So if you go back to the metric formulation, this is the part of the connection that influences what usually in the Pfefferman-Graham expansion you would have called G naught. And then the next component, the one with an L-1, will be TFI, and if you have higher spin, for instance, cases, so this is what you would call for the SL2 case, you will have this extra component, and just to illustrate how it works for the higher spin cases, then here, if you want to have a higher spin term current, it basically comes accompanied by the generator of that group element, the lowest one, and that generates that specific spin. Okay, so you can add here, there's a sum that you're entitled to add, which is relevant if you have SLN Chern-Simons. Okay, and the thing that we did then, so we focused then on the Euclidean black hole, which is a static configuration that satisfies basically the boundary conditions, i.e. meaning it satisfies everything that I wrote here, plus smoothness condition, or that people also call the holonomy condition. And so basically, a way, well, you can think of it as that the Euclidean solutions are a torus, where here, different color now, I'm going to identify in the solid torus the contractible cycle as a cycle that associated to the Euclidean time. So I'm thinking that Euclidean time is now periodic with period beta, or well, 2 pi beta. And And we impose an extra condition on these connections, and it's that the holonomy of A, and well, also repeat everything for A bar as well. So I'm just not writing it explicitly, but you do everything for A and A bar. And the path order exponential of this connection along this thermal cycle should exponentiate to the center of the group. Okay? And what this does is basically relate the sources that it gives you a relationship. It will tell you how the sources, the solutions to this equation basically tells you how the sources are as a function of the charges and vice versa. Okay? And the outcome of this, the nice consequence of imposing this condition is that this relationship between sources and charges is compatible with a first law of thermodynamics. So you will find, for instance, relationships of this source, where here the dot, dot, dot just means if you have a higher spin charges, there's additional chemical potentials and charges for those higher spins. Okay? And this term here, the entropy, there's a very nice expression for it. Very compact expression. So the entropy of the black hole will be 2 pi k. Here k, remember, it's the Chern-Simons level that I defined at the beginning, times the trace times L and LC. The trace of this lambda phi times lambda phi bar times L0. So what is this lambda phi and lambda phi bar? So lambda phi, the same thing for lambda phi bar, are basically, it's a matrix of eigenvalues of A phi, and this is the matrix of eigenvalues of I phi bar. Okay? So you get a very compact expression just in terms of the charges of the black hole. If you plug this in for SL2, so this is L0, the SL2 element. No, it's a matrix with where in the diagonals I put the eigenvalues. Yeah. So it's it's a fancy way how to just say that you have a sum over the eigenvalues where they are weighted with respect to the eigenvalues of L0. So L0 usually, this trace is taken usually in the fundamental, and so L0 is like something like -1 plus 1, or well, -0.5 plus 0.5. So that's it. Yeah. Yeah, so I'm always here static configuration. So for the purpose of black holes, I limit myself to just being static. Yeah. Yeah, so if you do this for SL2, I'll put here proportional because I didn't write down the specific coefficient, so it's just that I know it by heart. But this is basically something that will look like these eigenvalues, like for instance for SL2, and I mean here specifically the BTC black hole. You will get there's a 2 pi in front, and here divided by I think it's 6. Yeah, maybe I think this is the right coefficients. So you get this expression, okay? So that's what this equation means. But then it works also for all of the higher spin black holes in SLN theory, they will all have entropy that is of this form. And this expression was first, there's a very nice paper by De Boer with that they basically showed how you can derive this expression for the entropy, okay? They derived it from evaluating the free energy, the Euclidean Chern-Simons action, but originally it actually was not done like that. You can infer what the entropy is if you assume that this relationship between sources and charges is a thermodynamic relationship. You can basically read off what the entropy is if you impose that some form of the first law should be satisfied. So originally it was done like that. Like you basically infer what the entropy is as derivatives of the charges with respect to sources and so forth. You integrate up some of these thermodynamic relationships. But you can also do it more formally. Just compute the free energy, basically evaluate the Euclidean action, and you get it. What's that? It's this Chern-Simons level is basically what multiplies the action. And then C is 6 times K. Yeah, which is the Brown-Henao, is this 3L over 2G. Yeah. Okay. So just to give you a feeling, so I mentioned, so what is the status here? So in this context, just in this context over here, so first, as I already mentioned, it works super well. So this is all for higher spin theories, in particular, SLN theories. And HS lambda, it also works. It's a bit more complicated just because the algebra is more complicated, but it works as well. The thing that also here is super interesting that you can study and consider. Yes?
Elementary thing I'm getting confused about. Say, so E phi is a matrix. Both A and A bar are matrices, right? And when you write eigenvalue of E phi,
it's a diagonal matrix which has in the entries the eigenvalues of A phi. So I'm
the trace is actually summing over E phi to L0.
So, like for instance, for the BTC, this lambda phi is basically going to be some square roots of the mass of the black hole. Like one is positive, something like this, and you trace it. So this is lambda phi, and then L0 is like a half minus a half. And so you multiply these two matrices and then take the trace.
Why don't we just do trace of E phi minus A bar phi into L0? Why do we have to go to this diagonal basis?
Because there's a minus sign here. There are SL2 matrices still. And so the traces of lambda phi are 0. If I just put
the trace of E phi into L0. Why do we have to go to this?
An L0 in it? Or, sorry.
Sorry.
If I just take the trace of this matrix, the trace of this matrix is 0. So that's why I'm projecting it such that all the entries are summed positively.
But lambda phi is just a basis change from E phi, right?
Oh, yeah. It's just that you're putting it, you can write this in a way. There's a previous step where you can write it as in terms of the A phis themselves. Yeah. It's just that this is like the most convenient way, how to write it, how to compute it, just in practical terms, especially when you have higher spin cases. It's just a convenient way how to write it. But there's an expression where you write it in terms of the A phis.
If I wrote E phi into L0 trace of that would not be there. Minus E bar phi into L0. That would be the
naively, it will not work because you will have the matrix of eigenvalues of A phi in it. I can look up what is the expression that you need to write if you just write it in terms of the A5s. But
confusing is usually you take the trace for somehow you diagonalize one of the matrices and then you multiply it with another essential matrix and then you take the trace. That's kind of somehow seems basis dependent in but
well, this is not basis dependent, so that's why it's a nice way how to cast it, so you don't get confused about which basis you're using. So it doesn't matter how you implement it. If the physics of the boundary conditions is always the same, then, because you can do gauge transformations on these things and have decided to write them in some, like, not like some like silly way, like, so the reason why people like to write it here, because it makes manifest that your choices of basis shouldn't be important. But like when this paper is super nice. They do have the whole derivation of like the Euclidean action and basically the L0 comes about at some steps because they need to project against the charges. But there are in the intermediate steps you can see how this is just written like in terms of the ATs. As I said, I didn't write it down because at the end of the day we just use this equation and then. But okay. And I also wanted to talk about Wilson lines today. But okay. Yeah. So, so another thing that here is very interesting, and you can ask Justin about it, is that as you explore what happens to these conditions in a higher spin context, and you try to understand these holonomy conditions and the solutions to it, it gives you quite a very rich phase diagram. So you get phase transitions in additions to the Hawking-Page phase transition, which, to my knowledge, they have been understood from the gravitational context. I don't know if they have been understood in the field theory context. What is the interpretation of this rich phase diagram? But you get the typical Hawking-Page phase transition, but then when you're in the black hole regime, there's further phases that are particular to when you have additional charges. And then the other thing that I'm not going to, if someone is interested, they can ask me later. Another thing that you can do just in this context is to play around and also think about the role of what does it mean to be extremal in this language? So what is the notion of extremality in the context of manipulating the connections in this way? I will not give out the answer, so you'll have to ask me later on. Extremality? No, extremality is still static. Like for the BTC, it just means that you put the mass equal to the angular momentum. It's just a bound, like what is the saturation? What is like cosmic censorship? So what are like the minimal bounds that you can put on these configurations? And as well, this also leads to trying to understand if you have a supersymmetric realizations of this theory, you can as well ask the interplay between extremality and supersymmetry. So what does it mean to have a BPS configuration? But okay, so that's what I have to say about Euclidean black holes. So now let's move on to the second part.
For a general black hole, what will be the analog of this B formula?
What's that?
You take A phi at so should I think of this formula as being valid for a general black hole even at time dependent?
Time dependence, I'm not going to make any statements. This equation is valid for, like, it was derived assuming that you had a static configuration. The question of time dependence has, to my knowledge, has not been, and like understanding if you have some form of this formula for like some like kind of equilibrium. Yeah, I don't think it has been derived. or at least I'm not aware of it. But yeah, this is all this is like, if you go and look at this paper by Yan and Juan, like static from the get-go. Like, and mostly derived the word identities at the beginning, just to kind of set up the stage, but then when they discuss black holes, it's all like very static.
Does it need to be static or stationary?
Oh, well, stationary, I'm abusing, yeah, stationary. Well, without any time dependence, that's, yeah, so if you want, yeah. He says that the notion of stationary here, basically just, yeah, since you're treating all the time like A and A bar separately, like that's why I just said static, because, okay, I'm just saying that, oh, well, I just erase it. And in A phi, I just assume that all the elements are constant. And so, okay, stationary in this language will mean, oh, you do it for both A and A phi, sorry, A and A bar. That's, but it's not very, in Chern-Simons, I don't know how to make very well the distinction between these two. So, in practice, I just mean that the components of the connections are constant. Of the A phi connection are constant. Okay, so let's start. The first part of our discussion on Wilson lines. Yes?
In case of external black holes, to start with the formula that you have written, how is the A phi modified?
Yes, it is.
What happens in case of external black holes?
Basically, it's not diagonalizable, so I have to be a bit. That equation still, like, well, you go back a bit in some of the other forms of the equation. It's a little bit more tricky to. I wouldn't feel comfortable writing it that way, so I take a step backwards before I write it down. Oh, well, I don't write it like that. I just express the eigenvalues. But basically, extremality means that the A phi is no longer diagonalizable. So it has a non-trivial, like Jordan decomposition. So that defines extremality. And you can see how the holonomy condition, if the connections are not diagonalizable, the holonomy condition also collapses. Because you can't say that the integral of a connection along that cycle should exponentiate to the center of the group, because the center of the group is a diagonal element. And so what you see if you put in there connections that are not diagonalizable is that if you insist on trying to impose that condition, then the temperature necessarily has to go to 0. So that it kind of balances the effect of like the matrix being non-diagonalizable. And so that connects the two notions. But yeah, this is, so if you spell out what that trace is as a function of the eigenvalues, without writing it as trace against L0, you just write down, oh, it's the sum over the eigenvalues, then that equation is still true. In the extremal case, you just have to put that the eigenvalues are degenerate in a certain way, and then it's, yeah. So basically, these were like the two eigenvalues that you had, and one of them became, like for one of the matrices, the eigenvalues basically became 0. Okay. Very good. So, Wilson lines. Okay, now we have to change gears. So far, we in this whole discussion of Euclidean properties, we talked about global properties of the solutions. Right? We talked about the topology of the solutions, about the smoothness condition was like the main theme. But now we want to understand basically other properties of the solutions and properties that will be relevant to discussing Lorentzian features of the connections, okay? And ideally at some point, maybe by lecture 3, actually local properties of the connection. So the basic question, the way we started thinking about this, what we wanted to understand was this. So our question was back in 2013 is what replaces the notion of distance, and in particular, geodesics, and Chern-Simons theory. So when you're doing like a course in general relativity, geodesics are something that appear very, very quickly, almost like it's the first thing that you do as you're trying to understand aspects of the geometry. But in the Chern-Simons formulation, they're not so prominent. It's not, by no means, it's your starting point. And this is a basic entry, and we wanted to just understand, okay, what is the answer to this question? Now, the answer, it was actually for the case of lambda equal to 0, so for 0 cosmological constant, this was answered quite a while ago. It was answered by Witten, and also there's papers by Carlip. And just a spoiler, as the title says, the answer to what replaced the notion of geodesics in this case was basically Wilson lines. Okay? And so what I want to do now, for the rest of this hour or 40 minutes, I basically want to illustrate, I want to show to you how this works for the case of negative cosmological constant, okay? So how do you manipulate, how do you arrange things in the Wilson line such that you answer this question, and we see explicitly how this notion of geodesic distance appears in the case of SL2. And then we'll be able to as well answer what replaces the notions in higher spin cases, where there's not going to be a notion of geodesics, but we're going to say, okay, you should not be thinking about geodesics anymore, think in terms of these Wilson lines. So that was our motivation. So, okay. So, what are Wilson lines? So let's start with the loops, because in gauge theory, actually, people don't like to compute lines. They like to compute Wilson loops.
Statement that every Wilson line corresponds to geodesics?
No, it will not be that every Wilson line. Yeah, well, let's go through it, because I want to make this statement precise. I want to tell you exactly, because, yeah, let's write down what the Wilson line is, and we'll see that we have choices.
Some Wilson lines are geodesics.
Let me write down the equation, and I'll tell you what do we mean by some and how and what. So this is a loop. Sorry, there's a minus sign here that it's a bit. So the definition in gauge theory of a Wilson loop is this one. Okay. Now in Chern-Simons theory, because the connections are flat, this object actually depends on only two things. It depends on the representation R of the gauge group G, for which you're doing your, on which the Chern-Simons theory is defined by, and on the topology of the loop. It doesn't depend on the shape of the loop. Okay, so here the only thing that is important, because the connections are flat, is just the topology of the loop. So it's very similar. It's basically The holonomy was a precursor to this object. We didn't take the trace, we just did the path order exponential, but it's the same thing. The holonomy also didn't depend on the shape of the curve, it just depended on the topology of the curve. Yeah, so you define some topology for me, and then it's basically, you just, all the non-trivial loops on that topology, like, yeah. And so for instance, for the torus, I just have two. So there's only two loops, the contractible and the non-contractible one, yeah. And so if you pick some other curve, if you do some other weird shape, you just have to decompose it in terms of the contractibles and non-contractible loops, and that's all the information that you're going to get, okay? And it's an object that is very well studied in the context of gauge theory. Now, it's nice, this, one of the features when you have this trace. So
sometimes you also have to like thicken the curve.
What's that?
Sometimes you have to thicken the curve and how it twists, the framing, how it's framed.
Yeah, the framing will be, yes. Yes, those things will be important. We won't see them here, but because I'm going to treat the connections classically, so I won't see the framing comes as you try to quantize the theory, because you kind of have to break gauge invariance as you're quantizing. But yes, these things come in. As you view this as an expectation value inside of the path integral, you have to understand how these ambiguities arise. Yeah, but they're not going to show up. Well, treat A classically and just view this as a classical object. But the nice thing about this invariant for the loops is that, well, for this observable, is that this is gauge invariant, okay? So the trace basically, you exponentiate the connections, and then the trace basically removes any gauge redundancy. Okay. Well, gauge invariant under like small gauge transformations. If you have large gauge transformations, then the Wilson line basically tells you what are different, basically elements of the group. Now, we will be interested in computing Wilson lines. Okay, so it's basically that object. But I'll be considering some open path. Okay, so I'm not going to be thinking of a closed loop. I'll just be thinking like I'm going from some initial point to some final point. It will still be dependent on some representation. And this is, in terms of like how I wrote it up here, this should be viewed as basically a matrix element of the same path ordered exponential. So now I'll be integrating between the initial and the final point. And these guys here are basically states in R, okay? So it's basically like a wave function that you're computing. You pick states in some representation, and you'll be computing this. If you trace over all the states and you make the loop close, then you get up here, okay? So it's basically like an opening of this object up here. Okay. Now this one is not gauge invariant. It depends on the data at the endpoints. But this is the object that we're going to understand. Okay. So this is not fully. The loop is fully gauge invariant. The Wilson line itself, it transforms nicely. It has a covariant way how it transforms. But one thing that will, as we discuss this object, is that there's gauge dependence at the endpoints. Okay. But this is the quantity that I want to evaluate. We'll also evaluate this one in certain cases, and I'll show you this one is actually going to, well, if I get there, I won't get there, but just these two things are going to be related. can see as you compute things around a loop, it basically gives you that thing. Well, depending on the loop, of course, but the loop that is relevant for the horizon. So, okay, so Logan was already like asking me, okay, when, how does this work? Okay, so we want to make connections, we have to answer that question. And so the way that you think about that question is basically on this data that is contained in here. Okay, so we basically want to map the quantities, the parameters that are inside of this Wilson line to objects that we would associate to the geodesic. So the representation here, so I want to think in the following way. I want to think of geodesics as objects that come as you study the physics of probe particles. And in particular, massive particles. Okay? So this is one way how you can derive the geodesic equation. Just you write down the action for a massive particle and its dynamics. As you extremize the action for that particle, it tells you, oh, it has to obey the geodesic equation. So from this point of view, I say, okay, I have some massive particle. How can I contain the information of a massive particle inside of this object? The way that you contain the information of the massive particle inside of this object will be inside of this representation R. So this representation R that defines the Wilson line, we'll be trying to view it as basically a Hilbert space for this probe. And inside of this Hilbert space, well, the mass is one property that will characterize the Hilbert space, and I have to input that data of the mass inside of the representation. So the mass of the particle will come inside of the representation, the place where it could sit, given that we're looking at gauge groups SL2. The natural place where it can sit is basically inside of what defines representations, which is, in this context, the quadratic Casimir. So here, I'm thinking here of representations. Well, let's understand now which representations of SO2, 2 or representation. Well, we have to be careful. So M is a continuous parameter. So I want representations of SO2, 2 that have a continuous parameter. Because M is something that I can tune, right? I can pick whatever value I want. So if you start looking inside of representations of SO2, 2, the finite dimensional representations, I will look at irreducible ones. Of course, you can do whatever you want at the end of the day, but the representations of SO2, 2, which are basically two copies of... What is intuition for what?
Identification of the mass M with the quadratic.
Well, it's just that the representations for these type of gauge groups, they basically, no matter what, well, it's like I'm trying to think of representations of SL2, I'm trying to think, okay, what characterizes a representation? The Casimir tends to be...
But I'm just confused about why, I mean, you're missing something. I'm confused about the intuition behind the whole identification. I can kind of see that Wilson lines might correspond to 2-point functions, and maybe 2-point functions correspond to geodesics.
Yeah, I'll show you that, yeah. So that's another way that, but I'm trying to make that, yeah. So you can say, well, Wilson lines are known, just even from the gauge theory point of view, that their endpoints are charged states. Yeah, I'm just trying to pick that representation such that those charged states are something that I would have identified with charged gravitational states that obey the dynamics of a geodesic equation.
When you say quadratic Casimir is n, not n squared.
No, it's more, I'm writing just an arrow because I'm saying that they're related, but the Casimir is going to be m squared. the quadratic Casimir. Yeah, I'll write down what these relationships are. But let me specify a little bit more what the representations are. So in this, if I want this parameter to be continuous and be something that is tunable, the only representations in SL2 that have this, where you can store this data, are in infinite dimensional representations, okay? Finite dimensional representations of SL2. For finite dimensional representation of SL2, the Casimir is just a number. It will give you like 2 or 3, whatever, like, it's not a continuous parameter for finite dimensional representation. So this leads you very quickly, since this has to be continuous, to consider the set of infinite dimensional reps. Now there's many here, and I'm going to make a choice, okay? It has not been studied for all infinite dimensional representations. So if you're looking to do something in your free time on like a Sunday afternoon, you can try to understand what happens to the story that I'm saying for other infinite dimensional representations. But the one that I'm going to pick now, my favorite one, is the highest weight rep. Okay? So what is the highest weight rep? This is the one that, like, especially in the context of CFTs, is the one that we like a lot. So the SO2, so we've been calling, it has 3 generators, L0, L1, L-1. And the highest weight rep is basically parameterized by a highest weight state that we would usually just call H. H has the property that it has eigenvalue H with respect to L0 is annihilated by L1. And then the remaining states in this representation are basically created with L-1, whose eigenvalues are basically H plus N of this. And the Casimir, I'm using the blackboard in a nonlinear way, sorry about that. But then the quadratic Casimir is basically and for this representation is basically 2H times H minus 1. Okay, so this is the number that I'll be calling C2.
This is different from, like, when the entanglement entropy proposal was given by the potentiometer. I mean, like, they took just like a joint representation of SL3.
Yeah, but then we should, it's the same thing. Yeah, so with Eva, one of my PhD students, yeah, we both, so at this time, one of our motivations to answer this question was to make connections with entanglement entropy, and there were like, what had seemed at the time like 2 different proposals. They were also looking at what they call like a composite Wilson line, and they just picked some representation and then they evaluate it and they say, oh, this gives like something reasonable. So they basically guessed something. So one of my students then showed basically what they were doing. They will be computing the same thing that I'm computing right now, so that's why I'm not going through both sides of the story. The only thing is that since they had some intuition on how the answer had to look like, when I get to, there's some set of equations that you have to solve when I get there, and I'll just point to you. They basically noticed that for different SLNs, there was a convenient representation for which how you could solve those equations was made more easy. So they basically just guessed what the final answer of what I was doing. So, but here I'm kind of trying to motivate why would you have got there? But so yeah, so their choices of representations is just as I keep on writing this, is basically you will get some equations of motions for this probe, and they just notice like, oh, an SLN is easier to solve these equations if you use this representation instead of the fundamental. But that's why our answers were the same, because at the end of the day, it doesn't matter. There's some steps, some intermediate steps that it doesn't matter how you do the manipulations. But yeah, that representation here is not this representation here. It's just something about how you manipulate then the matrices inside here. You can kind of, the representation, yeah, I'll get there.
Impose that these representations should be some kind of unitary.
At this point, I did not impose unitarity, so that you can look at representations that are not unitary, and then try to understand what is the physics of those. I just like this one. That's all. I like the unitary ones, but there's nothing preventing you. I think this has not been explored.
In this set of infinite abstract unitarity is just greater than something.
Well, the norm of the states are positive, given that you define the Hermitian conjugate as just flipping the L1 to the L minus 1. So you give some notion of hermiticity, and then with that notion of hermiticity, then these states have positive norms. That's unitary. But I'm not making a statement of unitarity for the Wilson line. It's just a statement of unitarity of this representation.
That's a statement about H S plus I into half.
So no, there are representations. So you can also build unitary representations where H has, so right now I'm taking H as a real number, but there's also representations that allow for an imaginary piece in H, and they will still be unitary.
So that,
yeah.
So that's this continuous use in the
exactly. Yeah. So that's why I'm saying I'm not looking at all infinite dimensional, not all unitary representations. This is just one.
The discrete series, don't you again need H to be like an integer, like J into J minus 1 or something?
No, you don't need H to be, at this level, no, you don't need H to be quantized. The descent is, yeah. Maybe I'm missing something, or
I just remember, I must be remembering wrong, but there's a discrete series and a continuous series.
Yeah.
The discrete series has these numbers.
Yeah, but I'm not looking at the discrete series in particular. It's just that within the continuous one, you could allow for an imaginary piece.
Right, but the continuous one cannot have arbitrary H. I mean, there's some range of H's. Is that?
Yeah, but it's still.
I forget 0 to half.
Yeah, but it still gives me some wiggle room. That's a.
But there's some range of.
I just need the parameter. I don't need to I just want H to be something that is not fully fixed, so that I can. Well, you can also fix it if you want to, but I just want to identify this number. Like, I don't want it to be like a specific number. I want to think of this as basically like a conformal dimension, right? And be able to say, like, okay, this guy can have any conformal dimension that I want. So I'm just picking this highest bit rep. So this is the easiest one that just looks like a harmonic oscillator. I'm just saying, okay, at this level, H, I'm just picking it to be a real number. It's not going to impose. That's all I'm doing. There's bounds on it. But that's not going to be crucial for what I'm going to do next.
But somehow it should be true that if the story is true, that different representations correspond to different kinds of particles. Or something like that. Maybe some of them.
Well, they will correspond to particles perhaps with different statistics, or particles that will basically have different local properties, like how will they react to a diffeomorphism or things. So you can pick a representation, and then via the Wilson line, then you can say, okay, if I interpret this as a correlation function, what are its transformation properties under?
So from this discussion, I'm understanding that this has not been worked out completely for all the representations.
No, it has not been worked out for all of the representations. I kind of stopped here, and then, so we didn't study all of the representations, because with this, just making this point of okay, I'm looking for representations that have, this one gave us enough mileage to make a point. This is an interesting object. It connects with the geodesics. Yes, but there is more to be explored. Definitely. So, I always encourage people to do it, but so far, yes.
So states that you choose the UI and UF will have these scaling dimensions.
Yeah.
If I took xi and xf to infinity, then this sort of computes some correlation function.
Yeah.
Right? So
Of like some operators, yeah, it would look like a correlation function.
and so the correlation function of those operators was scaling dimensions at edge.
Exactly. Yeah. So you got to the end of the lecture. We're done. So, yeah. But okay. So from this context, basically, so I have 2 copies of SL2, so you kind of have to repeat this for the other copy of SL2 as well. And basically, so this mass that I was talking about, I'll basically identify it with the sum of the 2 Casimirs. If you wanted spin, it would be the difference between H and H bar. But this is also something, I'm not going to study representations that have spin, so I'll just put the spin equal to 0. It's also not needed to make a connection with geodesics. Geodesics are point particles that don't have spin, so it's not a feature that we need now. But it's interesting to study, just like you can, and then you will find the fifth, like you will find spinning, like the operators will be correlation functions of operators that have spin.
How do you fix this coefficient between H squared and C2?
I'll show you how. So now the task is. So the task is basically evaluate WR for this infinite dimensional representation. So, okay, so there's different ways how you can now proceed. So how do I evaluate a Wilson line on an infinite dimensional representation? Well, yeah. Yeah.
This continuous series, and I think you're right, of course this can vary continuously, and the Casimir is I think you take some number j to be half plus is, and then the Casimir is j to j minus 1, which gives you a real number, because it gives you 1/4 plus s squared.
Okay.
1 plus is.
Huh? 1/2 plus is
It's d by 2 plus is.
The 1 plus is is the normalization issue. So half plus is, because you want a minus 1 in its normalization, I think it's half plus is. So half plus is and half minus is, so that gives you 1/4 plus s squared. That's the number you want. But then I thought the angular moment, I mean the eigenvalue of L0 could be different. The eigenvalue of L0 could be some other number between 0 to 1, and then the numbers go down from there. So the eigenvalue of L0 is not tied to the Casimir in some tight way. Yeah, so I'm trying to, yeah. Is it? I thought that, there's a Casimir.
But do you agree, like if I define here, I have some highest weight state that has eigenvalue h, then this is a true statement. You can just check it for any of these HNs. If you compute its Casimir, we'll have Casimir 2h times h minus 1. This is just algebra. It's a little bit tedious because you kind of have to commute around the L minus 1, but this is like, I'm defining this representation like this. I'm saying start with a state that is annihilated by L1. And it has eigenvalue h. The rest of the states will have eigenvalue h plus n. The Casimir is this. Now, the thing is that what I have not spelled out is like, what are the conditions on unitarity? So we haven't been computing like the CAC determinant. Well, in this case, it's a very easy determinant. But so these conditions on what are the ranges of H just come as we try to compute the inner products of these states and trying to understand when the states are positive. But what my memory kind of, if I'm not like getting too old, was that if H was a real number, then there were no conditions. H just had to be positive. That's what my recollection tells me. Now, H can also be a complex number where it's like this a half plus I times S. And that also allows you to have the Casimir will still be real, and then you can also see what happens to the norms of the states in that case. But I'm pretty sure that if H is just a positive number, a positive real number, like, there's nothing wrong with this representation. In the same way that if you're doing this this is basically, like if I'm looking at Virasoro representations, this is like the baby-like version of the Virasoro case, where it's also the statement that the conformal dimensions have to be positive. If the central charge is bigger than 1, then there's no further restriction on like the representations of the Virasoro group, and you just get the typical descendants. So this is like even like a very kind of like, so that's why I like also this one, because it will make kind of a more natural connection with a CFT, like primary. But then again, there are other representations. I don't know what the representations are, how they fit inside of Virasoro. So that's why it wasn't for us like a super big motivation to study those other representations, because they're not like contained within the Virasoro, at least as far, maybe inside of Luvial theory they're in there, or I don't know, like there might be CFTs that allow for some funky stuff, but okay, just from this algebraic point of view, I think, yeah, you can study these other things. But yeah, I think, for instance, if you do this, so one of the questions I was going to have, like, also as a future task, I think if you do this for the sitter, then you need to consider things that are with imaginary weights. And that's how you get geodesics in the sitter. There will be non-unitary representations, actually. That's my guess. Nobody has worked this out, so please feel free to work it out for the sitter. But my guess is that it's kind of like a non-unitary version of this, just by an analytic continuation. But okay. So we need to evaluate this. And so there's two forms of evaluating this. And so there's the form how we did it historically, and there's the form that I wanted to explain in the third lecture. And now I always run out of time because I'm getting close to the hour. So the way we're at first very intimidated by evaluating this in an infinite dimensional rep, because it means that basically you have to understand how to do path order exponentials of A when A lives in an infinite dimensional representation. And I was terrified. Actually, then last year I learned how to not be terrified anymore, and it's actually not that bad. But initially in 2013, I was quite terrified of like the task of like computing this for infinite dimensional space. So we said, okay, let's do a shortcut, which was also something that was hinted in the papers by Winted and Carlip, but they only kind of went halfway through, in my opinion. So we kind of pushed this a bit more. And so we said, okay, so instead of thinking, so we're trying to compute some wave function or trying to compute a trace, we can trade this by, instead of computing the trace explicitly or computing the wave function as like this inner product, we can think of this in terms of path integrals. Okay, so let's try to understand how can we cast W of R, this Wilson line, as a path integral. And in this path integral, so basically when I will think about it this way, what I have to do is that I need to compute some action. I need to define some action for a probe that I'll call U. And as I quantize that probe, I have to argue that I'm getting this representation. So the quantization of U should give R. And this is easier because I'm better at constructing actions. I just want to use symmetries, and so that's what we'll do. So we're thinking, yeah, it will be a world line action. So I'm thinking of like this W. So now instead of writing those types of equations, I'll think that I have some path integral for this probe, and there's an action for this probe along the curve. And this action, basically, the way, so this is something that is kind of discussed in these older papers from the 80s. A way that is convenient to think of this action is as follows, is that there's two pieces to this action. If you want, there's a first piece. So let me local. So the way how you can try to design these actions is by first thinking of it as being like, okay, forget about the fact that you have a connection, that you have A, don't get distracted by A for the moment. Think of first trying to construct an action where you have global symmetries, well, where G, the gauge group, are basically the global symmetries of the system, and then the way that you input A is by making the symmetries local. Okay? And you just then have to argue, like as you build the system and you quantize it, again, that you get that the Poisson brackets will be basically compatible with the with basically this construction. And so particular here that the Casimir will be fixed to some number. So I'm just interpreting this as a wave function, and I'm saying, well, in quantum mechanics, I have two ways of computing wave functions. I can compute wave functions by just doing like the more like Hilbert space construction. I have states, and the wave function is just the bracket of two states. But in quantum mechanics, I can also think of that bracket as basically a path integral. So I'm just, instead of like thinking of it in like this kind of like state formulation, I'm just saying, oh, that wave function, basically where the path integral will have boundary conditions at the endpoints of that curve, the field will be like, so here you basically specify UI and UF as you're integrating over all possible configurations. You integrate over all possible configurations that start at UI and end at UF. So, and then, yeah. And then if I wanted to compute the trace, I would say all configurations for which UI is equal to UF, so that the field is basically continuous. Yeah. What's that? Yeah. Yeah. So I was going to say quite a bit about this action, just to kind of illustrate how you see that you get the right. No, it's just that like well, I can just write down what the final answer is, but a nice way how to try to understand like, oh, how do you go about figuring out what this action is that you first think of like, okay, I have some variable u, and you want to construct an action. Usually it's easier to just say, okay, what will be an action? It's an auxiliary variable. What's that? U is be something. It will be something that will transform under the gauge group. So we'll have a transformation.
Finite matrix or infinite matrix?
Well, in principle, it will be like an infinite. Well, if I do the. Well, I don't have to specify the represent. I just have to specify what is the action of the group on U. So, for instance, U. So, because I have two copies of SL2, so let me just make sure I have my conventions right. So, U is something that lives. So, I'll be thinking that this curve gamma is parameterized by there's some parameter little s that I'll call. So, U lives on this curve, lives on gamma, and it transforms like. So the gauge group has a left and a right action, and so this is basically, I want to look at basically objects for, okay, you can look what you want, but basically it has a left and a right action with respect to the gauge group.
Left is the SL2,
yeah.
H is SL2 and H bar is.
Yeah, but you could also have picked something different. You could have said, let me look at the infinite dimensional kind of representation and think of my fundamental variable as being actually x itself. But x it's not the x of the space-time. Like you can think of, just say, oh, let me think in terms of infinite dimensional representation. The space of functions like that live on SO2, or an SO2, 2 in this case. And so then you can think of like basically just in terms of the infinite dimensional representation. And then from that point of view, you get like kind of more clearly geodesic, like looking.
So how does the information about the representation R intend to?
As I quantize you.
Okay. So at this point, I can just think of it as a bifundamental of SL2, SL2.
Yeah, yeah. So the way I'm going to impose the, so let me just write down the action, and then we'll kind of stop-ish here. I'll just make comments about properties of this action. So for instance, so I'll write down the whole thing. I'm not going to do the splitting between the two parts. So we actually wrote it. It's easier to see what's going on if you write it in a first order formalism. So we basically introduce here, so U, as I said, is some bifundamental that transforms under L and R. P is an element of the algebra, and it transforms only under R. And basically, what I'm doing here is imposing a Lagrange multiplier that will tell me that the trace of P squared is C2. So it's basically, this is what's fixing the Casimir for me. And from the point of view of this action, this Casimir is any continuous parameter. So as I look at that constraint, that's what's going to be compatible with the.
P is breaking the symmetry between the left SL2 and right SL2.
There's also a P left. So this is what you will call like, quote unquote, the PR. There's also a P left. There's another conserved quantity that is basically U inverse. Sorry, no, U times P times U inverse. And because I actually can't distinguish between the two of them, it's the reason why I have C2 equal to C2 bar. So because it's the same P, so as I take the trace of P squared, this is what will tell me that C2 is equal to C2 bar. So this action already comes, it has two conserved, it will have two conserved quantities, but they have the same Casimir. Okay? So this action will be catered for representations that have C2 equal to C2 bar, and this is just a number inside of the action, so then it will not be a finite dimensional. As I quantize the system, it's not going to be a finite dimensional. It's just a Lagrange multiplier. It's basically, there's reparameterizations of the curve, and then you can basically fix this thing. So it's just a affine parameterization. And so from here you can, for instance, you can write down the equations of motions, and you can write down what will be the Poisson brackets, and then you kind of can then argue, oh, this is going to, as I quantize the system, this is what you get. In particular, so there's this object here, this ds. So this is basically just a partial derivative. So the quantization, I did it just for the case where you just have just ds being a partial derivative. But then as you want to make this symmetries local, so basically I want this to depend on S. As you make these group elements actually be dependent on the position along the curve, then lost it. You basically have to introduce these two connections. This covariant derivative, which are catered to the left and the right action, and so this A of S is basically the connection projected along the curve. Okay? Now, as you can integrate out, so when I write it like that, that doesn't look very suggestive of anything. It just makes very evident the choice of how my choice of representation is encoded. But one thing that you can do is kind of get rid of the Lagrange multiplier, get rid of P. So you can integrate out this momenta, and then this action. Looks like this. So it basically looks like a sigma model for the on a line, but well, doesn't matter. And this little object here, a bar with a little tool on top, is basically it's a bar, but where you view a bar as being gauge transformed by U. Okay? And so let me just get to this punchline. So when I write it like this, when I integrated up this action and wrote it like that, then you're like, well, it's getting kind of obvious, right? Because you will just tell me that you will have some Einbein, which is basically A minus A bar, and that action over there is just basically G mu nu, the effective metric along the curve. Now, one thing that is, it's there.
I should think of all this as too close to matrices.
Well, this is where it's interesting. For SL2, so if I do SL2, you can think of these as just for the purpose of evaluating things and like just getting your hands dirty. You can just think of this in the fundamental rep. Just put A being in the fundamental rep. Forget about this whole infinite dimensional representation, because the values of the actions are not going to really depend on which representation you use. So you can just put, this is kind of connected to what you were saying. So when you start solving just like, oh, I just want to solve these equations, then you can use whatever representation you want. And that's where it seemed that these two papers were doing different things, but it's the same thing. Because for the action won't care about which at this stage, if you just want to evaluate this on-shell action and tell me that the Wilson line is approximated by the on-shell action, then use whatever rep you want. So you can think of it as in the terms of like the fundamental rep, let's say. That's the one that I like to use. And so for SL2, yeah, you can pick the fundamental rep for the purposes of evaluating this and finding solutions. And the thing that you can do is just say, well, this U is now a distraction. This is actually an action for U, but you can notice that you can make the choice, you have the liberty of just saying, let me just fix U, and then view this as an equation for X. If I fix U, then the equation of motion there will be an equation of motion for U. So the equation of motion for U is basically the geodesic equation. And so you can say, well, let me write down, so you can write down the equation of motion for U. So you vary this action for respect to U, and you will get your favorite, like, geodesic equation with a 2. Then you get a commutator of the a's and the dx's squared, the x dot. No. So sorry, let me go backwards. So let's say you have this action. So then you find the equations of motions for U, and they look like this, which is basically, again, if you make this interpretation of this as being an Einbein, this is like the geodesic equation. No, this is an equation of motion for U. I varied with respect to U this action. If you vary this, I'm not varying it with respect to X. I'm varying it with respect to U, and I get something that you're very tempted to say it's the geodesic equation. But it's actually an equation for U. But now you can say, well, this is where the shape really doesn't matter, because this is not an equation for X. X is not a variable. X is something that I'm projecting the connection along with. And this action actually doesn't depend. You can pick different shapes of X, of mu. you will find that U will be different. It will not be 1, it will be some other value. But the action won't depend, like you will always get the same answer inside of the action. Yeah, it's just parameterizing the curve. But any choice of that curve that ends and starts at the same point will give you the same value of the action. But it's just that if I pick U to be 1, then this equation tells me, oh, if you make this choice, then X needs to obey the geodesic path. So it just forces X to be something, because you made a choice of what U was. But not because, but you don't have to make that choice. But if you wanted to really connect with the geometric interpretation, then, okay, you make this choice. Now, if for SLN, for instance,
write down this equation of motion and then put a certain value of.
well, it's just that this is the worst way how to try to solve the equations. So usually it's easier. That's why we also wrote it like this. It's easier to solve the equations like this. And so we actually, what we did is basically solve the equations when A and A bar were 0. And then we said, well, A and A bar are just pure gauge. So basically we can pick A to be like LDL inverse and A bar to be R inverse dr. And so we find first a solution to the system when A and A bar are 0, and then we make a gauge transformation to this value, and then it gives us a general solution. It tells us how the action, how the system responds if you do a large gauge transformations, because you know how it responds, because I know what happens as I do a symmetry. So I basically solve it for when these guys are 0, then do the large gauge transformations, then P and U change, and then I plug it in here, and I see what happens. So that's all that you're doing.
In this, where was this identification important of the quadratic asking within this calculation of the Wilson I understand?
Oh, it controls the value of the action in front.
But only that single number.
Yeah. At this classical level, if I'm just computing the action, it just pops up here. From here, this term doesn't contribute to the on-shell action, so it's just 0.
But you might have thought like you would get some violation of the equivalence principle at least in higher orders. So different masses would be a different thing.
Different masses will be, well, it just like, it will just.
So I see that number.
Ah, here. No, actually, you can, if I use different, no, if you use different representations, this answer is not going to change, if you do it carefully.
Why is that here? That's not here.
Well, okay, it's also hiding perhaps in here, because as I defined the C2, the trace that I used here was the same one. So, but it will cancel out. That data of that representation, I'm 100% sure. It's like we did it. Like we looked at how to solve the system in any like representation that you wanted, and it doesn't matter. Like it just doesn't matter. And so that's why there's at least 2 papers that did it in different representations, and we get the exact same value. So you might like don't get this like. Trust me, like things balance out, and it doesn't depend on.
That's good. I'm just really confused because this is not really a geodesic. This is more like some 2-point function of operators from masses.
Yes, yes.
It's true that geodesic probably really doesn't depend on mass. The 2-point function of a mass.
It will, and then the Wilson line will depend on that mass. Yeah, it will be don't worry. But tomorrow I'll show you how it is the bulk-to-bulk propagator, and then it has all the data in the right places, and it's just that here I'm doing a saddle point approximation, so that's why I'm only getting the geodesic. It's because I'm kind of like just approximating things, and then the correlation functions, if you do the same approximation, they're basically just the exponential of the distance between the 2 points.
In the 2-point function, the geodesic equation is dependent on mass. So the action is dependent on mass. Action of the geodesic.
Yeah. The geodesics don't ever depend.
That's the end in front. But in general, if you really compute the 2-point function, it will depend on the mass in more detail.
Yeah, and the
Again, it's true. The asymptotic part is e to the minus m, but then in general it depends on a more detailed way. So that should come out here, but maybe it won't come out in this expression. It's the fluctuations.
See, the thing with this formula, you can get the path, but
yeah, tomorrow I'll do that. From the path integral, Yeah, I don't want to do it with the path integral because it's quite difficult, but what the path integral, what is nice is that you can see why is this telling you something about like local physics, like how do you start getting this notion of distances and probing things like locally. So that's why I like to explain this path integral way, because it's for the higher spin cases, it also made it quite easier to understand what was going on. Yeah. But my only point here is that if you now do this, if I now look at SLN, actually I can never make U equal to 1.
But even here, I mean, really when we say E is A minus A bar, we really mean A minus A bar in some...
Oh, sorry, Twiddle. What?
Yeah, mean it in some gauge, right? I mean, you cannot just take like a vector potential of one gauge with another gauge with some time.
Exactly, but what U does, because U transforms under the... No, this is going to be super important for tomorrow, because U basically tells me how to relate the left and the right action. So so if A bar was only on the right, as I conjugate it by U, now it has an action on the left.
And then you can subtract.
Exactly. Yeah. This is that people tend to be very sloppy in the literature. How I was, for instance, in the first lecture, I was just saying, oh, I have 2 copies of SL2, and I use the same representation of SL2 for both of them. But basically what I'm doing is making a choice on how I relate the left and the right, and how I subtract them. Yeah, but people, even a lot of these papers on Chern-Simons theory and gravity, they're very sloppy, and they will just subtract L and R, like as if. But it's because they made a choice of what is the diagonal, and like how do you relate the 2 copies. But yeah, that's basically what this object is doing. It's telling me how to map left to right and how to tie them together. Yeah, so let me just finish with things for young students and postdocs to do. So things that have not been done and you can think about. So I haven't, yeah, there's a lot more that you can say here, but let me just illustrate some, like list some open questions. Just even in this path integral formalism, like tomorrow I'll give you more open questions as we actually compute the correlation functions and do a better job at this. Yeah, so to do. So these are not in papers. Nobody has written a paper about this. I am not working on this, so feel free to, so don't worry, I'm not going to scoop you or anything like that. But just to give you kind of like, if you're interested in this subject and want to kind of do something new, not just study what has been done, you can first, one thing is to do everything that I've done for de Sitter. For de Sitter 3, okay? So I already mentioned this. So in this case, the gauge group in Euclidean de Sitter is SO4, which you can view it as 2 copies of SU2. And you can have fun getting confused about physics and de Sitter, which is always interesting. But here also you have some luxuries that Chern-Simons theory with gauge group SU2 has been studied quite a lot. So there's a lot of results that you can use. You just need to understand how to translate them to the metric formulation. Yeah, they're very different. And so, but I think working this out will be very nice. Number 2 is also, as we have been discussing quite a lot, other infinite dimensional reps of SO2, 2. So there's been some work, but I don't think the list is not exhaustive. So this will be interesting. 3. Boundary conditions. So I didn't go through what happens to this answer, but basically the dependence on the endpoints comes in through the fact that U is always kind of like here. And so you have to say, even if you do it in this formulation or this formulation, you always have to tell me something about how U behaves at the endpoints. So there's the boundary conditions on U, that we pick them based on like, okay, I want to get a CFT correlation function. So the way that we chose those boundary conditions was kind of dictated by the fact that I already knew about ADS-CFT. So I'm like, I want to get a correlation function, and then I pick this value of U. But there's a nice interplay that has not been studied between the boundary conditions of U and the boundary conditions on A and A bar. Because as I also said in the first lecture, the set of boundary conditions on these guys are not set on stone. And so if you modify the boundary conditions on A and A bar, it's not clear what would happen to the boundary conditions on U, and like what are the rules, what are these physical choices. Because you can even be Machiavellic and pick U such that everything like cancels, which is basically picking states for which that the Wilson line doesn't give you anything. So you can definitely make bad choices. But maybe there's other good choices, and it's not clear what the interpretation is. Then number 4, I think this Wilson line has mostly been computed for like non-extremal black holes. But I think it will be interesting to understand how to evaluate W of R on extremal black holes, and basically try to understand a bit better how like something like an ADS2 region will appear, things like that. Also on conical defects, it hasn't been studied much. So basically, what I mean by here is use W of R as a more of an exploration of the interior. So you can evaluate this on extremal black holes. You can try to evaluate W of R to probe, as I mentioned in the first class, the inner horizon and singularities. This is tricky. The reason why it's not like this one is not so easy, and it's basically tied to this, to what do you specify for U as you go into the interior. So I know how to fix boundary conditions of U if the two endpoints are at the boundary of ADS. It's more subtle to understand how do you specify U if you're just ending somewhere in the middle, because you can change quite a lot the physics depending on what values you pick. So that's why these are not so easy, but worth thinking about. And then the other thing was, but I'll also mention it in the next lecture, but maybe just if I forget, is that as we try to move into the interior, it's also to relate the choices of U to, for example, TT bar deformations or JT bar deformations. So how would that be related? How would you understand the TT bar deformation of an ADS3 in this language of Chern-Simons theory? Given that Chern-Simons is very topological, and I told you nothing really depends on the radial parameter, maybe you can try to understand how these deformations, basically, if you make well-educated choices for U, how they would be interpreted as basically in this language.
To change even the boundary conditions at A and R.
Yeah, they would also, but this is where this whole interplay comes in. So you need to understand what are we doing here. No, TT bar has not been understood in the language of the Chern-Simons theory, because as I said in the first class, all radial dependence kind of drops out. So it's not obvious to me what is. Like, you have to do something to this little a phi, and it's not super obvious. And then for the Wilson line, as you compute quantities, you also need to understand how U will react to that. And I think that will be very nice to work out. So, sorry, I talked too much, but okay. Thank you. I'm done for now.